Minasan, konnichiwa. Zamurai Engineer desu. So in this live stream lecture, we will take a look at some of the examples in analyzing and or designing tension members. So using those what we learned from the concepts, principles, and from the point of view of the code, of the current code. So let us proceed with our textbook. This is by McCormack and Chernak. Before we go further, I would like somebody to confirm sound check. Do we have a clear sound? Okay. So very fast reply by Daniela, clear po sir. Shout out to you. Shout out to Daniela, which is actually our checker. Okay, thank you. So let us proceed with our discussion. So let us take a look from this author's perspective. What are the thought of examples from real engineering application? So just like what I'm telling you again and again, professional subject must have examples that are realistic. Okay, the same is my philosophy. So there are many professors which do not follow that philosophy and still trying to give you, for example, the board exam type of questions, and that is not bad either, but I am for the actual practice of engineering. And after you get those concepts and principles correctly, that's the only time that you can proceed to looking at the reviewers, looking at those hypothetical examples. So I am using these authors because they have these examples at actual engineering practice. So as a review, you have the elastic modulus of elasticity of steel, which is equal to 29,000 KSI here. So this equation is basic as it is from our structural theory and physics subject. We have stress equal to strain times modulus of elasticity. Okay, so this is constant. So in SI unit, can you convert this? What is the value? So I would shout out the one who can answer it the earliest. Okay. What is the equivalent of 29,000 KSI as the modulus of elasticity of steel? Okay, while you are trying to convert that or search for that, So already tackle this type of sections. So we already discussed nominal strengths of tension members. So tensile forces, nominal tensile forces. So we are through with this. We are through with this discussion. So rupture and yield. So these are the two major parts, because the third one, the blockshire, is just the combination of these two, yield and rupture. Okay. So we also discussed these net areas. So we have, I think we already discussed this part. We are through with this part. We are through with the effect of staggered holes. Okay. So workable gauges for angles. So these are the suggested dimension for the gauges. So gauges meaning the what? The distance of hole to hole. Okay. In terms of uh, longitudinal. No. Gauge is transverse. Okay? Transverse distance. Okay? So longitudinal is pitch, okay, or spacing. Nobody can remember or can convert the value of steel modulus of elasticity. In SI units. Okay. So actually we are through with this. We are through with this example. We are through with this effective area. We are through with this. So bolted members. So we already discussed, explained this table one by one, explaining it with respect to the effect of shear lag factor U. So already discussed this part, and we actually search for the table wherein we can show you the value of X bar. Apparently we cannot search for a table with that value for every section, for example, different types of section. Okay, so here is our example. Okay. So example number 6, we are asked to determine, really there's nobody who can answer what is the modulus of elasticity of steel. Okay, anyway, we are asked to find the LRFD design tensile strength, okay, and the ASD allowable design tensile strength. Okay, so there are two methods, ASD and LRFD. LRFD is what we call strength design. Okay, for a given W section 10 by 45, meaning with depth of 10 and with weight 45 pounds per foot, with two lines of 3/4 inch diameter bolts in its flange. Okay, so using A572 grade 50 steel. Okay, so grade 50 meaning Fy is equal to 50 KSI and Fu is 65. So that is the characteristic property of grade 50. So you can familiarize with that number. That would always come up. Okay, 50, 65. 50 refers to yield, 65 is ultimate. There are assumed to be at least 3 bolts in each line, 4 inch on center. So the spacing is 4 inch with respect to centers. Okay, 4 inch on center, and the bolts are not staggered, meaning it is aligned. Okay, there is no pitch. Okay, there is no pitch, that is aligned transverse. Okay, aligned transversely and with respect to each other. Okay, solution. So we can take a look at the table. So I would like to ask every one of you to prepare a table or open your table and take a look at the properties of W10 by 45. Okay, take a look. So according to Josh, shout out to you, 29,000 KSI is equal to 199 billion 947 million 961,584 Pascal. So therefore it is actually 200 gigapascal. Okay, that is what we are going to use, 200 gigapascal. So correct. Shout out to Joshua. That is equivalent to 200 gigapascal in SI unit. So I would like to search for a table that will give us, so while you are looking for the properties of that section, I would also like to look it up for myself. Where are the tables? Tables of section. So give me some time to open it. Take note, you can use interpolation in the table. If what you're looking for is not on the table itself. So you can use interpolation. Okay, so we have found the table that can I show you. However, it is not, I cannot share it, table. Why I am not able to share it? Oh no, I cannot share it. Okay, so previously, okay, I already show you this table, share log factor. So I will use this to show you the table of where it is located. Give me 15 seconds. So I think this is the one. See? Okay. Can you see this? So this is a table 3.2. Okay, so it is a table or in okay, so it is it's a very long table. Okay, figure 6.6 W section copyright AISC. Okay, so there are two types of design method, as you can see, ASD, LRFD, and the values for safety, omega 1.67 and 1.5 for LRFD 0.9 and 1.0. So we can use this table, okay, and look for the part that we are going to use in the example, that is W10 by 45. As you can see, this is around the middle. Okay, so how many? 1, 2, 3, 4, 5, 6, 7, 8. The 8th column, 8th row. On the 8th row, you can see W10 by 45. Okay, So, W10 by 45. What we need to get from the table, we need to get the gross area. So take note from the gross area. Okay, where is the gross area? There is no gross area. This is for what? Selection of ZX. This is there is no gross area. This is ZX. Okay, so plastic section value. So this is plastic section value, not the property for area and so on. So we have to look for the table. Maybe this one. Okay, maybe this one. Again, this table for plastic section. Okay, wait. So all of my tables are showing different thing. This is not the property. So let us look for this one. Let's look for another table. So opening a table alone is a waste of time. Actually not a waste of time because we are going to use it, but it's so time consuming. It is so time consuming. So we have what? At your screen, you can see the W section. Okay, so this is not from the code. This is from Continental Steel and Tube Company. Okay, let us find out if it will reveal what are the, so we have the different properties. Okay, so we have the different properties. So we have what? The depth, okay, the width, the web thickness, the sectional area. Okay, this is what we want, the sectional area, the weight. Initially, we have to confirm those weight and depth. Static parameters, we have what? Moment of inertia. So that's why you don't need really to calculate the moment of inertia in the x direction, moment of inertia in the y direction, section modulus, so section property. But this is elastic section property. So what we saw on the previous table is Z. So that is the plastic section modulus. These are Wx, Wy, these are elastic section modulus. So let's go back. We are being asked to find W10 by 45. So So let us take a look downward. So W12, we are now on W12, maybe on the next page. So we have W10. So we have W10 by 45. Here we have W10 by 45. So this is it, W10 by 45. Okay? So as you can see, just to confirm, W10 by 45 here. Okay? So in this line. Okay? So this is the W10 by 45. Okay? And to confirm, 10 is the depth. So here is correct. 10. The depth is 10. Actually 10.1. The actual depth. So that's why 10 is the nominal depth. Okay? The actual is 10.1. 45 is the weight. So this is the weight. So take a look. So it is correct. Okay? 45 pounds per foot. Okay? That is the weight. Now, what we need is the area. So area meaning this one. Area is 13.3. So 13.3 is the area. Here. So let us find out if that is what we are looking for. So 13.3. So you can see here. So area is 13.3. So from the table, 13.3. Why I am doing this with so much time? Just to show you the relevance. Because in board exam and in real life, in real design, you are not given this one. There's no one who will give you this. Okay? McCormack is not there. Chernak is not there. There's no one who will give you this. Okay? So that's why you need to be able to get these values from the table. So that's what I'm teaching you. Okay? Okay? From the board exam, you have to look at the questionnaires. Usually, the tables are placed at the back of the questionnaires. Okay? And if you are not aware, you will not be able to solve it. Okay? So you just have to pick up those values. Okay? 13.3 from the table. Okay? Okay? This is correct. 10.1. That is the actual depth. And BF, TF. BF meaning flange width. And TF is flange thickness. So let us take a look. Flange width and flange thickness. So there is no flange width and flange thickness. So we have the width. So this is the flange. The width is the flange. Okay. So 8.02. So let's take a look. So 8.02. That is the flange. So you have to understand it. Okay. 8.02. There is no BF in the table. but you need to understand that that is the BF 8.02. Okay, so that means you can get the value. Okay, so but in our table we cannot see the flange thickness. We have the web thickness here. We have the web thickness here, but we don't have the flange thickness. Now, since you have the width and the actual depth and the area, you can just solve for the flange thickness. Just solve for it, right? You know the web thickness, so just subtract from the total area. So I think you can do it on your own, okay? Because you have the area, just solve the area of the section, okay? Just solve the total area of this, okay? And then subtract it, and then you can divide by the width of the flange so that you can get the thickness. You can do it on your own. So therefore, you have the following. So there are different types of table. There are tables that are too detailed, and all of these are right on the table. Now we have to look at nominal or available tensile strength of section. Okay. So nominal from our formula. Okay. Our formula. So this is what? This is our yield limit state. So yield times gross area, therefore we have the nominal tensile force. So yield is grade 50, therefore the yield is 50. The 50 KSI multiplied by 13.3. So that's why we have this values. So this value coming out from the grade 50 steel. Usually they will give you A572 grade 50. They will not give you this and this one. You have to be familiar with this. So if grade 50 is given, so you know that it is grade 50 and 50 KSI is our yield. So also you can also see that you can approximate the value of ultimate by adding, for example, 25 to 30% or 40%. 25 to 40% of strength to your yield strength, you can estimate the value of ultimate. Okay. So multiplying these two, so you have what? 665 kilopounds. Okay. So kilopounds is kips. Okay. So letter A, gross section yielding. So using RIPdE, you have what? Yielding is 5.9. Okay? 5.9. So you just have to multiply by 0.9. This one. So this one, multiply by 0.9, you have 598.5. Okay? So just multiply 0.9. However, if you are using ASD, that is 1.67. Right? We already learned about this. You have to memorize this. You have to memorize this and you have to memorize this. Okay? So you have to memorize this one, and since you know that the relationship is 1.5, okay? So you can just constant is 1.5. So you can just memorize one set of equation. That is what I'm doing because I have to save memory space. Okay, I do not memorize this and this at the same time. I memorize one of them and then use 1.5. Okay, so because 1.5 divide by 0.9, use your calculator, that is equal to 1.6 something. Okay, 1.6666 and so on. So that means that is 1.67. Okay, that's how I do it so that I could what? I could save memory space. I'm telling you, I do not have any memory. Okay, so letter B for our tensile rupture strength. Okay, so we need the net area. So this is our gross area minus how many holes there are. At least 3 bolts in each line, 4" on center. So there are 3 bolts. Okay, so okay, but we have what? 4. Oh, this is what? We have maybe a typo error, no? Okay, as you can see it, there are assumed to be at least 3 bolts. So at least, maybe more. In each line, so there are 2 lines. Okay, so there are 2 lines and 3 bolts on each line. 4" on center. This is the distance. So the author mistakenly picked up the 4. Okay, this 4 is about inches and not about the number of bolts. How many bolts? 3. So this must be 3. Okay, this must be 3 and not 4. Okay, okay, so I can show you author's mistake. Okay, actually this is not actually consciously made by the author. He knows it. He is an expert, but he overlooked. Instead of using the 3, he used the 4. Okay, the same manner you can do it in your board exam. This type of mistake. Okay, so we are going to what? Subtract the bolt holes. That's why, what is this? This is the bolt hole diameter. The diameter of the bolt is 3/4 plus 1/8. This is the allowance. Okay? So this is the allowance. If you are using the code, you are going to use 3/4 plus 1/16. Okay? Do you follow? So this is the number of, or the diameter of the hole times the number of holes must be 3 multiplied by the thickness. Okay, so this is the thickness of the flange because the flange thickness is found out to be 0.62 inches. Okay, take note. I am telling you, you have to solve for that flange thickness because the hole is located on the flange, not on the web. As you can see on the table, this is the web thickness, 0.35. This is the web thickness. This is not the flange thickness. Okay? You have to solve for it. Okay? Okay? So our table doesn't show the value of the thickness. Okay? So, assuming that you already solved Do you know how to solve the area of this one, the cross-sectional area? It is just a simple algebra to solve this cross-sectional area. Okay? So, and you do not know the thickness of the plants. You know the height, you know the width, you know the thickness of width. The only thing you do not know is the thickness of the flange. Therefore, you can solve it. One equation, one unknown. Okay? And assuming that 0.62 inches is correct, so you can put it here, multiplying the diameter of the bolt hole so that you can have the area projection of the bolt hole. Area projection of the bolt hole times the number of bolts, which is supposed to be 3, subtract it from 13.3, which is the gross area. That would be our net area. So let us do that. So using our calculator, let us do that. So where is our calculator? Casio calculator. Casio calculator. Oh my goodness. You cannot see it, but I'm quite distracted by too much notification. Giving me too much notification, and because of that, the notification obstruct my visual point of view. How can I set this notification into 0? There are thousands, hundreds of notifications. Okay, so we have a Casio calculator. So let us compute. Let us compute that starting with 13.3. Subtract 3 holes, quantity 3/4, 3 divide 4, plus he is using 1/8. McCormack is using 1/8 as an allowance, multiply by 0.62 inches. Okay? Press equal. The value must be 11.67, not 11.13, because we are only using 3 bolts. So the answer must be 11.67. Okay? Do you follow? So that's why I'm telling you, I found so many mistakes from the book. Okay? By just studying. Okay? So referring to tables in manual for 1/2 of this, or that is what WT, T section. T section meaning you get 1/2. 1/2 of 10 by 45, that is 5 by 22.5. Okay? If you look at that table, okay, you can see X bar. Okay? So X bar is what? That is our, what do you call that? That is our, in calculus, that is centroid. That is our centroid. Location of centroid. Okay? So I do not think we have that in our table, the location of centroid here. So there are tables that you have that. However, we do not have in our table right here. Okay, because this is a table for W plans. Okay, so you can look it up, or you can solve it using your calculus, or using mechanics. That is centroid, the theory of centroid, the principle of centroid. You can do that. Okay, and then length of connection L, 2 times 4. Okay, so because there are 3, the author is correct by having 2, because there are only 3 bolts. There are 2 L. There are 2 L. There are 2 spacing. Okay? There are 2 spacing. You have 3 bolts. So there are 2 spacing. 1 and 2. Okay? So there are 2 spacing. Okay? And the spacing is 4 inches. So he is correct. But he is wrong here. No? So L is correct. 2 times 4 is 8. Okay? And then from table, again, case number 2, okay, we have this table. I already shown you this. Okay? Maybe I can show to you a different table. I'll show you a different table. So maybe I would have to show that table again. Okay, this is the table. Okay, so table case 2. So look at the case 2. So U is equal to 1 minus X bar over L. Okay, so therefore, since we can solve the X bar, which is what? The X bar is point. Okay, so you cannot see the X bar. So I have to. The X bar is 0.907. So X bar meaning centroid. You can do it. You can solve the centroid. Okay? So after solving the centroid, put or substitute the centroid here. So I already show you the formula. Case 2 is equal to 1 minus X bar over L. Therefore, you have this value. Okay? Do you follow? Do you follow? Okay? And since this is the value of U, but as you can see, 8.02 is the value of flange width, okay, and 2/3 D. Okay, put up this expression and compare with our flange width. Okay, so 2/3 of D. Okay, so we know that D is 10.1. So 2/3 of that is 6.73. Okay, so from the table again. Okay, so from the table again, case number 7. Okay, let's go back to the table. Okay, from the table, case number 7. So let us show you case number 7. So this is our case 7. 2/3. Okay, sir, where did you find this expression? This is the expression. So 2/3 D. So our flange must be compared to the expression 2/3 D. It could either be greater or less than. Okay? So, after comparing the plans, we found out that 2/3 D is less than the flans. Therefore, we will have U is equal to 0.9. Okay? So, U is equal to 0.9 because of that. Okay? Case number 7. Okay? Do you follow? Do you follow? So, 0.9 is our value for U. And if we use case 2, it is the same. The same value if we use case 2. Again, if we use case 2, the value is still 0.9. Actually, 0.89, which is just 0.9. Okay? Okay? So imagine that these estimates are actually showing us that they are actually reliable. They are just an estimate. They have an error, but we can see that they are reliable. We can cross check. So 0.89, 0.9. So we can cross check. So we can use 0.9. Therefore, so and therefore we can what? We can just substitute it from our equation. So effective area is just equal to U times net area. Therefore, we can solve this. And because we have the wrong value for 11.13, that is supposed to be 11.67. So 11.67 times 0.9, our net or effective area must be 11.67 times 0.9. The correct answer would be 10.50. Okay, 10.5. Okay, and because we already have 10.5 multiplied by 65. Okay, so our answer would be 683. Okay, so the correct answer would be 683 as the nominal. Take note. Please correct your example. This example, please correct it. The answer would be 683. Okay? Keeps. 683 keeps. And if you multiply by what? 0.75. Okay? LRFD. Sir, that is 0.9. But we are actually what? Tension. Okay. On our rupture, we are looking at the rupture. This is point. So 0.9 is for 0.9 is for, you cannot see it. So here, so 0.9 is for gross. Okay, this one gross. Now for rupture, we are going to use 0.75. Okay, so 0.75. So therefore, multiplying by 0.75 for our LRFD, the answer would be 512, not 488. So the answer is 512, correct to 3 significant figures. Okay, any question? Any question? Do you follow? So 512 is the correct answer up to the 3 significant figures. Okay? So Compare that. 512 is our answer. Compare that to the gross, which is 598. Okay? 588. Okay, 598 versus this is actually 599, correct to 3 significant figures, 599 versus 512. Which one is lower? So the lower one must be our answer. Okay? So the lower one must be our answer. So the lower one must be 512. So 512 is the answer. Okay? You have to compare it. Compare yield and rupture. Okay? To take note, for rupture, you have to use 0.75. I already showed it to you on the theory. Okay? On the theoretical discussion. So, show you 0.9 and 0.75. Okay? Okay, any question? So, any question? You can do the same thing on ASD, but rather than multiplying, you have to divide. Okay, so you have to divide. So if you divide, the same condition must result, meaning rupture controls. Meaning the rupture should control. Can you give me a minute? Can you give me 1 minute, please? I will just drink water. Alright. Okay. Okay. So let us compute that on ASD side. So by what? Dividing by 2. Okay. So divide by 2. Must have the answer. The answer would be 455 rather than 325. The answer is 455. So compare that. Compare that to our answer on the yield. Okay. The answer on the yield is 398. Okay. So 398. Do I get it? So the answer is 11.67. 11.67. Okay, here the answer here is 11.67. Then times 0.9, because we have 0.9 here, times 0.9 here, we have 0.9 as our value of u. Okay, times 0.9 and multiply by 65 times 65. Our answer is 682. Okay, and then divide by 2. Divide this by 2 because we are ASD. So in ASD we have to use the safety factor 2. So safety factor is 2. Therefore we have to divide this by 2. The answer would be 341. Answer is 341, not 325. Take note, 341. So compare this 341 to our yield, 398. So therefore, 341 is the answer. Okay? So the final answer would be 341 here on the ASD. Okay? So what we can conclude about this, in table 3.2 K7, it is stated that Q may be used equal to 0.9 for W sections if, so that is what we used. Okay, so case number 7. Okay, for W section, if flans is equal or greater than 2/3 D. That's why we computed 2/3 D. Okay, and number 2, answers to tensile strength problems like this one may be derived from table 5.1 of the manual. However, okay, the values in this table are based on the assumptions that U is equal to 0.9 and effective area is equal to 0.75 times gross area. Right? Okay? As a result, values will vary a little from those determined with calculated values of U and effective area. Okay? Okay, do you follow? So, if you calculate effective area with this code provision, it is actually different because what we did was to multiply AG by 0.9. We multiply AG by 0.9 actually. Okay? And 0.9 and 0.75 are not the same. So we will have different values. Okay? For this problem, the LRIPdE values from tables 5-9 are 599K yield, and actually this is 512, no? 512 for rupture. Okay, so those are the explanation that, okay, two engineers would give two different answers. Okay, one would use this one, okay, which is the assumption from the code also, and also this one, which is also a code provision using the table. And the third one, you can actually compute U, which is equal to 0.89. Okay, so there are three values actually. Okay, so as we already computed 0.89, but we use the table K7. If we use case 2, the value is 0.89. Okay, and if we use the conservative assumption of the book, 0.75, that is already totally different matter. Okay, totally different values. Okay, so next is we'll just complete this example before we go to the break. So example number 7, we are asked to find out the LRIPdE and ASD design for A36. Okay, 36, A36. So A572 and A36. There are two types of material that we are using in this book. Okay, A572 is the current trend. A36 is the old trend. Okay, which is the old one. A36 is equal to what? 36 KSI yield. Okay, we can estimate the FU by using 0.25 or 1.25 to 1.4 multiplied by 36. So we can estimate that to be 50. So FU is actually 58. Okay? 58. So you need to familiarize yourself. So you have to even memorize A36 is equal to 3658. A572 equal to 5065. Okay? So you can memorize it like that. And we are given what kind of section? Angular bar 6 by 6 by 3/8. So this means we have 6 inches on one leg, another 6 inches on the other leg, and 3/8 inch in thickness. That is what we mean by this angular bar. If we are using angular bar, that is how we decode the name of the bar. If we are using S section, W section, T section, they are using a different name coding system. Okay? So, leg by thickness. Okay? So, at its end, so it is connected at its end with one line of 4. So, there is only one line. 4 7/8 inch diameter bolts in standard holes, 3 inch on center. So, center to center distance of holes, 3 inch. So, how many holes? 4. So, 4 holes. This time, 4 holes and 3 inch center to center. So, reverse. No? Reverse. Previous example, we have 3 holes, 4 inches center to center. Okay? But now, it is connected on one leg of the angle bar. Okay? So, with this given, we can take a look at the table again and look for these values. When look it up, you can look it up because this is what? Symmetrical angle bars. We have equal values for Y bar and X bar. These are centroids which you can solve. Okay? So, gross area is also on the table. If not, you have to solve this because we can clearly solve this. 6 by 6 and then the thickness is here. So, you can solve it. So, anyway, you can use the table for this, and with these values, nominal or available tensile strength of the angle could be computed. Okay? So, since this is grade A36, 36 KSI multiplied by the gross area, so we have value 157.7. So, let us show that to you so that we can check also if there are errors. So, let us check. So, we have 4.38 multiplied by 36 because 36 is the strength. Okay? So, the answer would be 157.7 or 158. Okay? So, since this is what? An intermediate computation, we can use 157.7. Okay? That is the same with the book. Okay? Next, let us now proceed to the mode of failure, yielding. So, cross section times yielding. So, let us multiply this thing by 0.9. Okay? Multiply it by 0.9. Still, we have value 141. Okay? I will show you again. Multiplying it by 0.9. So, we have 141.9. Okay? Same with the books. answer. Okay. Now let's proceed to the next. We are now going to solve for the effective area and tensile rupture strength. So for net area first, let us use the gross area minus. Okay, let us subtract. So now we are going to subtract the whole. Why it is minus 1? Okay, why it is minus 1? Okay, so there are how many holes? There are 4. Actually, how many? How many is the given? There are 4 holes, 3 inch spacing. But why we are using 1? Because the 4 holes are located longitudinal. Longitudinal is the location of holes, and we are calculating rupture strength. So since we are calculating rupture strength, we are going to take a look at the transverse axis. Okay, transverse. We are looking at the transverse axis, and since the alignment of the holes is longitudinal, there are 4 transverse weakest link axis, weakest link lines. Okay, one for each hole. That's why we are going to subtract 1. Okay, that is the reason. Okay, take note. It's very important to understand this thing. Okay, and then bolt hole, bolt diameter plus allowance. So bolt hole, and then multiply by thickness. So it is given. The given angular section is 6 by 6 by 3/8, meaning this is the thickness, 3/8. Okay? So you can check if this is correct. So let us check it out using our Casio calculator. So let us use the gross area. So the gross area is 4.38. 4.38 minus the hole diameter, which is 7/8 plus 1/8, that is 1. 7/8 plus 1/8 is 1. Multiply by thickness, which is 3/8. That is equal to 4.005 or equal to 4. Okay? Sir, where did you find out the bolt diameter? From the problem. Let us find out. From the problem, we are given the problem here. This is the bolt diameter. 4 7/8 inch diameter bolts. Okay, so 7/8 plus 1/8, that is 1. Okay, that's how we find all the given. Okay, so when you have the complete given values, you can solve for the net area, which is equal to 4, then solve for the length of connection. The length of connection, there are 4. So there are 4 holes. How many spacing? There are 3. There are 3 spacing. So 3 spacing. How much is 1 spacing? 3. So 3 times 3, we have what? 9. Okay? Take note. I am explaining this as detailed as possible, line by line, one by one. Okay? I am explaining all the new concept and principle. I am not explaining all the old ones, the prerequisite. I'm not explaining the prerequisite. You have to do those. You have to have your own responsibility to be prepared for what? Centroid and so on. So that is
the previous subject. Okay, so 9 inch. So we have L, and we can find out the X bar, which is what? What is the centroid of L? So the centroid is 1.62. You can either solve this by using the centroid concept. You can solve this by calculus, by mechanics, okay? So, or by using table, right? And then X bar divide by 9, then subtract the result from 1, so you will get 0.82, okay? After getting the 0.82, you can take a look at different cases from the table. Okay, so let us use our table. Using our table, so case what? Here, case number 8. Case number 8, meaning single and double angles. Okay? So, it is definite. It is not W, it is not M, it is not S, it is not HP. So, it is what? Angle. So, angular. So, this is our case number 8. So, just like what the book said, case 8. Okay, for 4 or more fasteners in the direction of loading, use 0.8. Okay, so with 4 or more. So since we have 4, okay, or more, so we have exactly 4, so we have to use 0.8. We already saw 0.8 and we have 0.82 here, so we have to use the higher one. That's the same thing, just like we did on the last example. We have 0.89 and 0.9, we use 0.9. We have to use the higher one, no? We have to use the higher one because we have here, okay, we have to do the effective area, okay? We have to use the higher one. So 0.8 and 0.82, so use 0.82. So 0.82 times 4, so we have what? Okay? Like that, okay? We have 0.82 in our previous computation. On case 8, we have 0.8. So compare 0.8, 0.82, use 0.82, the higher one. Okay? So therefore, our effective area is 3.28. Okay? So just multiply the net area with 0.82. Okay? And after solving that, therefore, we can solve the nominal tensile force. Okay? So 3.28 multiplied by FU. Okay? Take note, don't use 36 because this is FU. We are solving for rupture. Solving for rupture, we are going to use FU and not FY. Okay, so FU 58 times this one, so 190.2. Okay, and because we have that, what's next? Now we can proceed with LRD. For rupture, 0.75. Okay, for ASD, 2. So let's show you. Okay, so therefore 0.75 multiplied by this, you just have to multiply. So just have to multiply 1.42 or 1.43 is the answer. What? Answer is 1.41. Another type error. What's happening? Okay. It is yielding. So compare 1.43 versus the yielding. Okay, so the yielding is 1.42. 1.42. 142. 142 compared to 143. So therefore, the answer would be 142, which is the lower. Use the lower. Sir, why we are using the lower in the strength? Because that is the capacity, the safe capacity. That is the safe capacity. There are two capacity. So this is the weaker. This is the weaker capacity. So we have to use it so that we are sure. We are sure that this will also satisfy rupture. We have to satisfy all of the failure modes. So we have to satisfy rupture. We have to satisfy yield. Okay? So if ever, we have to satisfy block shear. We have to satisfy bearing, strength. Okay? So we have to satisfy all of the failure modes. Now, we can do that by selecting the lowest value. If you select the lowest value, that value would satisfy all of this. Okay? Similarly, 142 satisfies yielding. 142 also satisfies rupture because the rupture is 143. So therefore, 142 satisfies 143. And not the other way around. If we pick, for example, if we pick 143, 143 satisfies rupture, but it does not satisfy yielding, meaning the material cannot resist 143. The material cannot resist 143 thousand pounds of load. That is what we mean. That's why we are using the lower one. Okay? Okay? So that is the reason. For ASD, just divide by 2. So 190 divided by 2, that is 95. Okay? Or 95.1 if we have 3 significant figure. And then compare this to the yield. The yield is 94. The yield is 94. So therefore, in this example, yield controls. On the previous example, rupture controls. That means the rupture value wins. This time, the yield value wins. Okay? The yield value is the lower value. That is what we mean by wins. Okay? The yield value is the lower one. That's why yield controls. Okay? So we are through with the problem solving for yield and rupture, failure modes of tension members. I would like to wait for your questions. Any questions? Do you have any questions? If there are no questions, is there any question? So if there are no questions, so let us take a break. So 30 minutes break, and let's be back again. See you next live stream. This is Dr. AP, preaching engineering for nation building.